Welcome to module 30 of database management systems. We have been discussing about indexing and hashing, and this is a concluding module on that. We have in the last module discussed about different hashing techniques, static and dynamic, and compared that and introduced bitmap indices. Now, in this module we would specifically look into the use cases. We will check as to how indexes can be created in SQL first, because you will have to use it. You have already known the theory of various different indices and so on. So, how do you actually tell the system to index? And the second is the important thing as to when should you index and on what. So, we talk about a few guidelines for indexing. So, that is what we want to learn. So, index can be defined in SQL in a very similar syntax as you create a table. So, you say create index, put a name for that index, and then you say on which relation are you indexing, and put the list of attributes on which you are indexing. So, if branch relation can be indexed on branch name, and I may call that B index. Now, there is a way to also express create unique index. If you say create unique index, then it will expect that the search key is a candidate key, because in the sense all values of that will have to be distinct, unique. Now, this used to be very common to do this kind of indexing earlier, but now it is more preferred that you can use unique integrity constraint in terms of the create table, which we have already discussed, and that will ensure that you have that kind of a condition satisfied, and you may not create unique index for that. If you do not want an index, that you do drop index and put the index name. So, most database system allows specification of the type of indexing and clustering that you want to do. So, you can create an index for a cluster also, and you can create index for composite index for multiple columns. So, let us run through quickly a couple of examples. Create an index for a single column to speed up queries that test that column. So, we are saying employee EMP tab is a relation which has an attribute ename, the employee name, and we want to create an index on that. If we do that, then any search that is based on the employee name will become really fast. Now, while you create the index, you could also use optionally various other factors which relate to particularly the storage setting. You can set what is the storage you want to keep for the index, how you would like to increment that, and so on. What is the table space, and very most interestingly you could say that compute statistics. Now, this is something which is optional, but is very useful. For example, if you are not sure as to how your data is getting distributed in different relations and how really they are queried, you would not know whether an index is good or it is inappropriate. So, it is good to actually compute that statistics in terms of the index, that you want to know that by doing this index what kind of accesses have happened. So, compute statistics will tell the database system to keep on computing this, which you can subsequently refer to. You can create index on two columns also. So, here we are showing one where EMP tab is indexed on employee name, ename, and employee number together. So, he is saying that you create an index on both of these and compute the statistics at the same time. Now, other ways there are index that can be created on functions. So, suppose if there is a query which is going to sort based on the uppercase writing of the ename. So, if I just index the ename, then that itself would not speed up the operation, because while you want to sort, then the ename will have to be changed into the uppercase by upper, and that is every time you will have to do that for every record, and then actually apply the sorting comparisons. So, that will become a slow process, but you can do a function based indexing where you can specify, as you can see here, the function based indexing, where you say that you index based on upper e name. So, what will happen, your actual values are in possibly lower case or mixed case, but your index EMP upper e name will get created on the in the order of the upper case of e name, and will be very useful in terms of the sorting later on. Now, you can, like the normal index, you can also create the bitmap index. So, you just say create bitmap index on the name, and rest of the structure is similar. So, if there is a student relation which has these fields, we can create an index on gender, we can create another index on semester. These are very typical candidate for bitmap index, because gender can take 2 values here, male and female, semester can take 4 values 1, 2, 3, 4. So, the bitmap are shown here, and then if I want to do a select where the gender is F and semester is 4, then it is basically ANDing the bitmap of F, which is 0, 1, 1, and the bitmap of semester 4, which is 0, 0, 1. So, if we AND these two, we will find that we have the result which is 0, 0, 0, 1. So, which tells me that the student ID, the 4th record of the student ID 103 is a result. So, this is how bitmap indexing can be used in SQL, and actually this the whole thing can be used subsequently in multiple key access. For example, if you are doing a query where it's you have department name is finance and salary is 8,000, then there could be several strategies for processing this query using the index values. For example, if you have single index on single attributes, so you can use the index on department name to find instructors which have department name finance, and then test if the salary is 80,000, or you can use index on salary to find instructors with salary 80,000 and then test if department name is finance, or you can use department name index to find pointers to all records that pertain to finance department, index on salary to find all records that pertain to 80,000 salary, and then take intersection of the both sets to get the final result. So, multiple key access could be achieved in terms of various single indexing, single attribute indexing also. When we are doing composite search keys, then naturally if there are 2, then the indexing means that you will have to define a combined lexical order. So, department name salary means that either department it is ordered to indexes are ordered in terms of just the department name, or if the department name is same, then they are ordered in terms of salary. This ordering in which you write the attributes in the multiple composite search key is very important, because you can see that for the 2, if the department name is same, then the salary will be compared, but not the other way around. So, when we have index on multiple attributes, say again going back to that same example of department name being finance and salary being 80,000. So, using separate index is less efficient, though we saw how that can be done, but we can also efficiently handle if we have this indexing on department name and salary, then we can also easily handle queries like department name is finance and salary is less than 100. It is not, because as you can easily figure out, because if I can find the equality, then I also know what is less. But note that we cannot efficiently handle if I say that where department name is less than finance and balance, I am sorry, this should be salary, salary is 80,000. The reason is that the ordering of the attributes in this composite key is department name salary. So, if if department name is less, then there is no way to check for the equality of salary. But if the department name equals, then there is a possibility of checking on the salary. So, because of this ordering, this will may fetch many records that satisfy the first one, but not the second condition. Now, you should also remember that you need a special privilege to create an index, because this is partly in the domain of the administrator's job. So, you need the specific privileges, access rights to be able to do that. So, to create a new index, either you have to own own that those set of tables on which you are creating the index, and or have the index objective privilege for those tables, or the schema that contains the index must also have a quota, so that you can, because creating the index means you will be using the temporary table space on a regular basis, and but with this you will not be able to create index in some other user schema. For that you need a global rights, which is the create any index kind of system privilege. So, also check if you are not being able to create an index, check what is your privilege that exists. Function based indexes require other privileges, please check on that. Now, let us, so we have seen how to create index, how to use that in terms of the SQL application, SQL query system. Now, we will quickly take a look into how should you index and where. So, if you recall in the modules 16 to 20 in the week 4, we have studied various issues of a proper design of relational database system. We focused on normalization of tables that can reduce redundancy and minimize anomaly. How can we easily adhere to various constraints, how to improve the efficiency of access and update. A better normalized design often gives better performance. For example, we are optimizing minimizing the requirement for computing join and all those. So, those advantages we have saw, but the actual performance of a database system is significantly impacted by the way the physical data is organized and managed, which does not come across in terms of the logical design that we have seen. So, these are what are being achieved in terms of indexing and hashing. So, this is where we need to understand the actual boundary to the physical organization, and that is what we have been trying to do. So, if you think back, while you are normalizing at the design level, so those are the startup time activities. So, usually you will design and normalize and make the create table and do all that at the beginning of a database system, and it will really be changed later, because it will have severe implications. But the performance behavior will continue to evolve, will continue to change, because the design does not tell you exactly what the statistics of the data would be, what the behavior of the data would be. So, it will evolve as database is used over time. Hence, you will need to continuously collect statistics about the data of various tables to learn of the patterns as to which table is getting heavier, what are the attributes on which more accesses are happening, what kind of queries you are getting, and you have to adjust the indexes on the tables to optimize the performance. So, that is the whole requirement all about. Unfortunately, unlike the functional dependency or multi-valued dependency theories that we have studied in the design space, there is no sound theory that determines optimal performance. So, all that you have is more an expertise that you develop through experience. So, what I will take you through are a set of few common guidelines about how to keep your database agile while you go through the life cycle of different data coming in and going out. So, the first rule, I say rule 0, is the indexes lead to access update trade-off. We have already seen this, that every query results in a search in the underlying physical data structure, as we have understood. Having specific index on search certainly can improve performance, but as we have already noted, every update, whether be it insert, delete or update of values, will result in update of the index files. So, it is an overhead or penalty for quicker access that we are paying. So, having unnecessary indexes can cause significant degradation of performance. Index files will also occupy significant space on your disk, and it may actually cause to slow down your behavior due to memory limitation during index computation. So, rule 0, indexes lead to this trade off, always be watchful about that. Use judgment to index. Rule 1, index the correct tables, decide which tables are best candidates for index. To creating an index, if you frequently want to retrieve say less than 15% of the rows in a large table. Now, of course, 15% is a ballpark number, this can vary greatly according to the relative speed of the table scan. Faster the table scan, you can use a lower percentage of cutoff, more clustered the row data, you can use a higher percentage for cutoff. Index tables, index columns used for joining multiple tables. If you have situations where multiple tables are used in joins on a moderately regular basis, then the columns that are used in the join in these tables should be indexed based on those. The primary and unique keys automatically have indexes, but you might want to have an index on the foreign key. So, consider that. Small tables do not require index. If a query is requiring unnecessarily long time or unexpectedly long time, it is time to check if the table has become really big compared to small, and it might be time to index that. So, rule 1, index the correct tables, and certainly related to that is index the correct columns. The columns with some of the characteristics I have just noted down are good candidates for indexing. Values are relatively unique in the column, then indexing will give you good benefit. There is a wide range of values where your regular indexes will work well. There is a small range of values where bitmap indexes will give you good results. So, use those. A column contains many nulls, but queries often select all rows having a value. So, there are columns have not of null values, but whenever you do a query, then you actually take out rows which have values. So, in those cases you can actually, if you involve certain, if you write the SQL query by keeping the condition in a way so that the index can be used, that is, for example, you could put a condition such that only non-null values will be matched. Compared to that, if you had just done a non-null check, your first query would run faster if you have an index on the call x, because the query would be able to work on that index. So, these are things that you should do in terms of the column. And if a column has the kind of characteristic that there are many nulls in the column and you typically do not search non-null values, then it is better not to index those columns. Long and long row columns cannot be indexed anyway. So, remember the rule to index the correct columns. Then the rule 3, limit the number of indexes for each table. The more the index, more over it. We have already seen this as a part of rule 2, rule 0 as well. When rows are inserted or deleted, indexes of the table must be updated. When columns are updated, all indexes on the column must be updated. So, there is a lot of cost. So, have as limited number of indices as will serve your purpose. So, you must regularly weigh the benefit of having the indexed for queries against the performance overhead of the updates. For example, if a table is primarily read only, you might use more indexes because the overhead will be less. But if a table is heavily updated, you might use fewer number of indices. Rule 4, choose the order of columns in the composite index. So, you have already seen couple of slides back, I took you to the impact of what is the impact of ordering in the columns in terms of composite index. So, the order of columns in the create index statement can affect performance. So, the column that you expected to be used most often, put that as the first index, because it is also possible that you are actually not doing a query which takes the whole of the composite search key, but a part of it. But if you have a composite search key index, you will still benefit if the query is using the attributes from the first part of the index. So, here I am showing some example, say there is a vendors part table, and let us say there are 5 vendors, and let us say so there is vendor ID, part number and unit cost. Forget about unit cost for this consideration. So, it is primarily part number and vendor ID. So, let us say there are 5 vendors and each vendor has about 1000 parts. So, and let us say that it is queried like this, that the part number is such and such and vendor ID is such and such, you select all that matches. Now, if you create a composite index, then it should be on part number vendor ID, not the other way around, because if you do that, then queries where only part number is used will also run faster. But the vendor ID here is not a very good candidate for indexing as a first attribute, because it has only 5 possible values, very small number of values. So, indexing really does not help here, it cannot discriminate. After indexing, there will be lot of clusters still found. Rule number 5, gather statistics to make index usage more accurate. That is a very important factor. The database can use indexes more effectively if the statistical information is available. So, gather statistics, learn from that. We have already discussed how to gather statistics from the create index statement, and then there are functions. These are function names in Oracle. In your system, you might want to check up what these functions are called. So, by that you can find out statistics about the tables and the schema that you have, and use that information to subsequently optimize the index. The last rule, rule 6, is drop index that are no longer required. So, if an index might be dropped because for several reasons, for example, it simply does not speed up the queries. So, table might have become too small. There might be many rows in the table, but very few index entries, right. We have seen these are not the ideal. So, it may not have been the case earlier, and now it may be the case. So, in that case, that index should be dropped because it is not helping you. The queries in your application do not use the index. The query, you have certain indexes and the queries are done on other attributes or other composite attributes. So, it is not, the index is of no value, and obviously, index must be dropped before being rebuilt. If you are rebuilding, if you are creating a new index in a new way, then so make a judgment and drop indexes which are no longer required, as and when you observe that, in drop indexes and improve the performance. When you drop an index, all extents of the indexes segment are returned to the table space. So, this is basically the space management, and SQL command for this you already know. Now, please keep in mind that if you drop a table, then all associated indexes are automatically dropped, because obviously, if the data is not there, then how about their index. So, to drop an index, you need the drop any index system privilege. We talked about privileges earlier too. So, this summarizes our discussions on indexing and hashing. So, here in this particular module, you have learned to create index in SQL and introduce few rules for good index. Overall, in this week, in all the 5 modules, we have learnt about how to speed up query processing, how to speed up the execution of access, insert, delete queries in your database through the lifetime, and we have looked at various different indexing schemes. We have looked at hashing and made comparisons. So, one take back that you can certainly have is the most important indexing scheme or indexing structure is the B plus tree, which can be used for data files as well as for index files, and several like SQL Server uses the B plus tree only. Now, hashing options we have looked at, and we have seen that it has a varied acceptability. It is a powerful technique, but not all systems use that equally strongly, and we have then understood that indexing a database or tables on different attributes is a very delicate responsibility, which has to be done with a lot of judgment, and for that statistics must be rightly collected, and good judgment in terms of the distribution of the data, access of the data, nature of queries, all these need to be considered carefully, so that you can really get good performance from the design that you have. So, on top of the knowledge of good design that you acquired through all the theory of normalization and redundancy removal, your good judgment in terms of good appropriate index design will take you a long way in terms of making a very good database system engineer.